Hi everyone, welcome to the YouTube channel for Physics 2500 Intermediate Mechanics at the University of Windsor. I am Dr. Hammond. So we've now completed the analytic portion of the course, and so for the next 2 weeks we will be discussing how to implement numerical solvers for solving your first order and second order differential equations. So up to now, we're doing everything with pen and paper, or maybe you were, entering things in Wolfram Alpha or something like that that could solve an analytic solution for you. But now we're actually going to develop our own numerical solvers and use the built-in solvers to show how to, integrate first order and second order differential equations in homogeneous differential equations and also plot them. So I'll also be uploading these slides so that you guys can follow along, but also as part of this video I'll be discussing these slides. So why we want to use numerical solutions or develop numerical solvers is that sometimes differential equations are quite difficult, especially once we get to inhomogeneous differential equations where there's some energy term, and also we can have nonlinear differential equations. And that's some of the work that I do for my modeling as part of my experiments. So these are actually quite common problems, and now with how easy it is to program these things and how quick it is to solve, I think it's really important that you guys can develop these tools for your future physics careers. So so far we're using Newton's laws to solve for equations of motion. So we put in the different forces and we get what the acceleration is going to be, but then the acceleration of course is the second order derivative of position, and what we actually want is the trajectory of these particles, and so that means that we need to solve for the velocity, so we integrate once, or the position, so we integrate twice, and sometimes this integration is quite difficult. Yeah, when we have something, as we say here, what if the source term is varying in position or oscillating in time? It's actually quite a common problem. We've looked at damped systems, but you can also have a driving term. So if you have a driven damped system, trying to understand intermediate states of this is actually quite difficult to do analytically, but with a computer, it's very easy to do. And so that's why we wanted to be able to develop these numerical solvers. Also, this will be a good foundation for your programming skills for your careers after you've finished your undergrad here at University of Windsor. So this is just a really powerful tool that all we need to do is when we develop a really general powerful solver, all we have to do is put in the initial conditions and we'll be able to solve our ordinary differential equation. So I'm using Python because it's free. I've been using MATLAB for a while, which I find a really convenient language to use, but full MATLAB with all the toolboxes is something like $3,000 or something like that. There are student versions that are $50. I think there may be $60 now for students. And they're quite good, but they're missing a lot of the toolboxes. So if you're trying to do something more complicated, such as image processing and things like that, you can't get that. So that's one thing. Nice thing with Python is everything's free on it, and so everybody has access to all of the libraries that you might need. You can also, if you like that programming language, you can also use Octave if you've ever heard of that. It basically replicates what MATLAB does, but it's not nearly as fast as MATLAB. The plots that come out aren't very good, and I've found that it does crash quite regularly, so maybe I'm not recommending that strongly. For Python, I use Anaconda as for the distribution. It just can manage the packages and things like that. Some people like programming with Jupyter, which is like a notebook style, which is actually quite useful if you're working in a lab or something like that, where you can make comments on what you're doing and then plot some data that you have, and then analyze that data immediately below. That's really useful for keeping notes. For these things, though, we're going to be using Spider. It's a Python environment. It's nice. It basically mimics how MATLAB is set up, which I find quite intuitive, that you can just have your code. If you want to make some small changes to a variable or something like that, you can do that offline, and the plots are fairly easy to use and manipulate and things like that. And also it's easy to get all of your variable information. So if you're not sure if you're defining your arrays properly or something like that, or you have some large matrices you want to look at, it's really easy to look at that data. So if you haven't already installed Anaconda, I highly recommend it. I think you have all supposed to have been using Python for Physics 1500, that from Symmetry to Chaos course. But if you, for some reason, don't have it, I recommend that you download it. I just go to anaconda.com, download, and you should be able to download it for whatever operating system you have. So for those of you who are using Spider for the first time, I'd recommend that you do a couple of things for it. And when I fire up Spider in the next video, I'll be showing you how to do these things. But I find Spider doesn't by default remove variables from your previous run, so I like to make sure that that's done. And so you can just go to Tools, Preferences, and when you click on Run, there'll be a General Settings, and you just remove all variables before execution. I find that fairly handy because sometimes I'll do something offline that I think is actually part of my code, and then I'll forget about it. Also, if you're plotting things for the first time, you'll find that your plots show up on the bottom right-hand side. It's just these little plots, but you can't click on them or do anything with them. I like them to pop out in a separate window, and then that way I can easily save them or manipulate them or whatever I need to do. And so you can do this by going to Tools, Preferences, and select IPython Console, and in Graphics, choose the graphics backend to, instead of inline, choose Qt4 or Qt5 or something like that. And finally, Python, instead of using toolboxes like MATLAB does, it imports packages. So this is common for some other programming languages such as C and things like that, where you can import libraries. You can import this matplotlib, which is a common plotting library, and you can, instead of calling matplotlib every time you want to plot something, you can make it a shorthand and just say you import it as PLT. And so that means if you need to make a plot and you're calling this library, you can just say plt.plot, and then it'll plot something instead of calling this whole library every time you're doing it. And same thing with numpy. So numpy is a common numerical package. It does the same thing as scipy, which is a scientific package, but I use numpy. And so you do numpy dot, say, cos or numpy dot sine, and that will give you a sine of, or a cosine, calling the numpy library. And I also like to start my code all with plt.closeAll, and that closes all the previous figures because, as I said, I like them to pop out in their own separate windows. But then that means that if you don't close them, then after running your code several times and debug it, you end up with a whole bunch of popped up windows. All right, so with this, I will fire up a new video that will talk about, that will show you an example using Spider.